Okay, go ahead. Thank you.
Yeah. Hi, I'm Wojciech. I hate pineapples on the pizza. And for the last 2 years, I've been working as a formation on some cool projects like Membrane and LiveCompositor, so-called React for live streams. And today I want to share a few tips that we learned along the way on the low latency multimedia processing. So before we go deeper, let's start with what really LiveCompositor is. It's basically a media server for real-time video composition, video and audio composition, where you give some inputs how you want to actually compose your streams via HTTP requests, send your streams via RTP. Video compositor composes it and output the streams for you. So in this talk, we're going to go from this black box approach and delve a little bit deeper into how it works internally. So let's get started. Firstly, we need to receive our streams. And we've implemented RTP receivers, and there we hit some first issues. We've observed 50% packet loss even when streaming on localhost. So what's the deal? Firstly, we get these issues only when streaming with RTP over UDP. The first few packets were always correct. Many Linux packets were less. And it only happened on Linux, worked fine on macOS for some weird reason. Any guesses what might be a problem? Okay, so we hit UDP buffer overflows. And this wasn't the first time we did it. We hit it a few times earlier in the membrane as well. And by default, UDP buffers are quite small on Linux, only 200 kilobytes around that. And if you got a keyframe on the beginning and a lot of B-frames next, you can easily overflow it. And the solution for that was firstly increasing the UDP buffer size. But since this required a lot of privileges over the operating system, we can base our working on that because we don't know if user has that privileges, give that privileges to LiveCompositor. So we sped it up reading from the UDP sockets by having a separate threads that only read the data from the UDP socket and send it for later processing. And one of the reasons why we hit those overflows is because we expected our streams to be something like evenly spaced frames sent to us, but in reality, it was more of the second case where we had a lot of data coming in batches to us due to some bufferings, user buffers, and so on and so on, and sometimes in wrong order. So when you are building some real-time processing pipelines, you have to consider that as well. Okay, we've received our data. Now we have to decode it before working with it. And here we also made some issues, some problems related. Firstly, we tested performance on some test sources, like FFmpeg test sources or Ustreamer ones. And decoding and encoding those videos is much cheaper than decoding and encoding real video because you get low variance. So we get a false impression over the performance of the decoders and encoders. And then when we tested it on like real videos, we had to change some defaults to get the right performance. So you should use big bag money for testing, obviously. Another low-hanging optimization fruit in this process is using hardware decoding and encoding. So instead of using the CPU-based implementation, you can use GPU-based one. And if you use something like FFmpeg or Ustreamer for that, it's pretty easy to change from one to another. And for us, decoding and encoding was one of the most expensive part of the whole pipeline. Like usually you hit over 70% of CPU usage on just those two parts. So with hardware decoding and encoding, we can also reduce the copies between the CPU and GPU, reduce the sizes. And it's especially important if you do something like computer vision models in our case rendering, because instead of sending the raw video frames. You just send encoded video, decode it on the GPU, work with it, encode it back, and send it back to the CPU, and it's much cheaper. However, this requires a lot of more work than just switching your encoder, and there is a lot of research going on right now on this. So we've decoded our video, but before rendering and mixing the audio, we have to some kind of synchronize streams, deal with such things like some streams dropping, some streams giving us a lot of frames at once, and so on and so on. And in our case, Q does that. It basically has to deal with like network instability and with problems like overflowing RAM by decoding eagerly all frames at once. So what we did? First, we use buffering for we add some small latency to the pipeline, and then we can handle some invariance in the network, and we don't get like lagged streams or jitter streams. We just we get a nicely smooth stream by adding some latency, and the back pressure is to reduce the RAM usage. Basically, what Q does is tells the decoder that if it decoded already enough video, then it doesn't need to decode some more frames at once. Yep, it can wait. So let's say we synchronized the frames, the audio. Now it's time to render and mix it. And in order to optimize that, we did a lot of pre-allocating memory optimizations. A lot of you might think that decoding memory is really expensive. What is really expensive in this part is not decoding itself, but usually the allocating the memory, because you have to interact with the operating system and so on. So for the compositor, we use pre-allocated GPU textures for like the whole pipeline, so we don't have to allocate multiple textures on each render. And for example, in audio pipeline, we use a lot of pre-allocated array buffers stack a lot of pre-allocated array buffers for performance reasons, for like audio resampling, audio mixing, audio decoding. And before we even delve into the optimization, we firstly have to detect what really is the problem and profile it, because otherwise we're just doing guesswork. So while doing that, it's important to do it on the hardware that you will be actually running the software in the end. What we did wrong is that we imagined that the LiveCompositor will be always run on the machines with the GPU. And then we had a client that wanted to run it on the CPU cores-only machine. So while on the GPU rendering was negligible, rendering cost was negligible, on the servers with emulated GPUs, it turned out to be like 70% of the whole pipeline. So we have to optimize for that. And what we did, we basically reduced number of renderers per frame, like rendering some static elements only once, like text and images, and flattening all the diffs to render them all at once. So you don't get those each pixel calculations multiple times. So, okay, we've encoded our video. Now we have to send it and audio. And you might think that our journey ends here, but it actually is a bit longer, because we need to receive this video on the other side. And in a lot of cases, it will be received by some form of player. A lot of players work in different ways. And you have to keep in mind that the SDP handling might be different, or, for example, audio PTS values might be discarded. If you are having an audio pipeline and you caught audio in the middle of it, some players might just discard those PTS values and play it right after, right? So you need to fill it with silence, and you have to keep in mind that. So, and This is basically the pipeline we scrape the surface of it. But it's really important to ask the right questions before we solve such hard problems, because adding the real-time component adds a lot of complexity into the system, and optimizing those stuff is also quite resource intensive, right? You need to use a lot of developers for that, and it might be not the best way to solve your problem. So those have to be real time. For many business cases, you don't actually need to do those things live. An example of that is we're having a project that does WebRTC recordings, right? You would think that it's totally live real-time case, but what you can do is just save your RTP data that was given to you, and then after the session, stream it and compose it in offline mode if you don't need this recording right after the session. This gives you a few benefits, like, for example, you don't lose frames while with using UDP. You can use TCP for sending data. You can process all of the frames without dropping them in the queue, and you get the frame precision. So I think it's worth figuring out what do you really need a real-time part. And because of the other part of the infrastructure is really important, because you can optimize the processing part itself, but in a lot of cases you will pay much higher bills, like 2-3 orders of magnitude larger for CDN infrastructure. And we actually had one project that was like a copy of the Twitch, and there the CDN part was much more expensive than the processing part. So even using high-level language like Elixir was fine, because it's just a bucks compared to the thousands of dollars, right? Okay, anyone want to see live demo? How it works? Okay, so let's get it. This one. Session. Okay. So firstly, we get some live stream demo. And here we see some stream with our camera working in real time. And we should say that it works with some pop-ups. This one is quite interesting, because in LiveCompositor we don't only give you the high-level API, but also access to low-level features of the rendering tools. So we have like stream on the green background, and you can remove the background with your code and render all the text and all the other stuff with just using Compositor API. Okay, I have to close the. Don't see this. Sorry for the streaming. Okay, before I end the presentation, I want to make some announcements. So firstly, after 2 years of hard work, we finally have the API that will show that it's stable, and you can check out the source code on the GitHub and use it if you want. We iterated through many versions of the API, starting from like rendering graphs, and right now it's just high level, similar to HTML API. And we are organizing RTC on conference, the second edition of it. Last year was awesome with some talks from Lorenzo about bandwidth estimation, Michał about WebRTC, Elixir WebRTC, Chavi about text slice and CDN logs, and many others. Great talks. So if you are interested, this next edition is 11 to 13 September. And you can subscribe to the newsletter that gives you 15% additional of the all ticket price. Currently, we have 50% off on very early bird tickets, so this will give you another 15% on top of that. And this newsletter will give you will send you some dev tips and tricks, something like number of membrane Mondays, if you've seen on Twitter. If you're interested in that kind of content, you can check it out. Also, some materials, what happened in the multimedia world, and monthly summaries on everything that happened in memory. So thanks a lot. Those two QR codes are there. If you have any questions, I'm open to answer them.
Thank you, Wojciech. Amazing presentation. So are there any questions for Saul first and Mark next?
Hello. Amazing stuff, mate. Thanks for sharing. I have a question about, so you mentioned one of the optimizations you did with like flattening divs, which somewhat suggests that there is some markup involved that may or may not resemble HTML. Can you maybe give us a little glimpse on when you composite this, how do you express this? Is it a custom DSL, HTML?
Yep, sure. Actually, I can show the code just right. Maybe we're more interested in that. Okay. Hope it's there. Okay. So basically, this is like registering all the outputs and so on, and for like specifying what actually is rendered, you use something like this. So it's like HTML in JSON, I would say. It had to be really weird because it's like it's the media server after all, but we tried to get the HTML vibe and feel familiar to web developers. So we actually take that high-level specification, and then we transpile it to like our mediary representation. We optimize that. That goes into the render graph that is actually rendered on the GPU. So that was the optimization I was talking about. So yeah, it looks something like this. You have some components, and you can actually do things pixel perfect, and also use some built-in components. Like for example, this one just lay out the input elements in the grid. So it works like a little bit like this.
Hello, great stuff. You mentioned the processing savings using GPU. What kind of GPU was it? Is it discrete, consumer grade, or something more niche? Or did you do any kind of cost analysis savings on the cost per watt?
Can you repeat the last question?
Did you do any kind of cost analysis savings on the costs per watt?
Okay, so The GPU is just standard like GPU that you can use on your developer machine as well. It's basically any other modern GPU works fine with it. It just have to implement some features that basically all new GPUs do implement, like from the last 5 years. And for the optimization, we didn't delve that deep into optimizing rendering itself, only those flattening this stuff, because if you think about it, and if you think what GPU is actually rendering, for example, in like video games, right? You get the crazy stuff. Here we only have like 3, 4, or 5 planes or something like this rendered all together. It's nothing to the GPU really if you compare it with like Cyberpunk or something like that.
Hi, thanks for the presentation. A follow-up to that, are you running LiveCompositor on cloud? And I guess have you looked at like cost of using GPU instances versus using the just compute on a regular instance?
Yeah, so for the cloud, we don't have like production yet running on the cloud, but we tested deployment on the AWS and the whole deployment process. We haven't tested like the costs of the GPU versus CPU, but we have one client that is going to run the video compositors solely on CPU instances with just 2 cores, so and they spawn each instance per user, so you can do even something like this. And then they are emulating GPU on CPU, so you can also run it without GPU.
Any other questions? Okay, thank you very much, Wojciech.
Thank you.
Amazing presentation, thanks.